Okay, guys, I am pretty much ready to go now. So I will change the scene to be this one, I think. Yeah, there we go. Okay, so everybody can see me on the screen?
Yep.
Yes, okay.
Yeah.
Hello everybody, welcome to the tutorial for the final exam tutorial for 768 computer networks. First things first is like my notes are available for this course. They're not completely done, but you can visit my website, which is www.tutor.ca/notes, and you can find my notes there. Most of the course content, I just didn't finish the last lecture notes, but there's videos on that too that I posted there. And so today the plan is basically just to go through a couple problems that are interesting and probably related to final exam content and kind of use that as discussion here. And then from there we can do some questions that we find from other places. It's fine, we have 2 hours, so however you want to fill that. This is recorded and I am recording right now, and I will be posting this on my YouTube channel, which is just my name. So just search my name. So if you just search on YouTube, just search Adam Saba, and it'll be posted there, just like my midterm tutorial for this course was as well. And yeah, that's it. Yeah, and the notes, sure, PDF as well. I'll put it in the description of the video, the PDF of this live stream here. So yeah, how many people we got? We got a lot. We got 75 people. That's good to see. So yeah, we'll start with some questions that like someone's asking if we start with some heavy questions while our brains are still fresh. That's a good suggestion, right? It depends on what you guys consider heavy questions, right? So like yeah, what like I was planning on starting with just kind of like a MAC address one where we have like the broadcasting happening throughout the network, which could be something we could do. That's probably where I was going to start, and then I'd move on to just the professor's slides like that, where like the final exam slides there. So why don't we start with that? And but yeah, I guess I'll ask just generally to the group, like what do you guys find the most difficult thing that you want to review here to be? Computer networks. That's a fair point. Yeah, selective repeat questions, CSMA, CA, yeah, that kind of stuff. Yeah, for sure. So for that, yeah, we can definitely talk about that. I've spent the last day or so or 2 days kind of reviewing as well, because I'm also taking this final exam. So we'll hopefully tackle these questions as a group sometimes if needed. But yeah, spanning tree questions, subnets, where they give us the order of sender receiver and we have to complete the diagram. Yeah. Second group, third group questions. Yeah. Okay. Sounds good. So why don't we start with this one just to kind of get things going, and then we can work from there. So first question here is, we have this collection of LANs here, which are connected by switches, and we want to complete the MAC table for the switches using like the whole broadcasting thing. So let's start with this kind of as a warm up, and then we'll move on. So the tables look like this, right? So it's like this for each of these switches here, if it gets a packet like from S3, then it knows what port to send it to, right? Whatever port it's going to be. And this gets, assuming it starts empty, it gets filled in iteratively using whatever the transmissions are, right? So we'll kind of follow through here with this. This could be a question on the exam where you are given the sequence of transmissions and you want to fill in the MAC table with it. So yeah, let's go through what's going to happen here, right? So the first thing is S2. Oh yeah, by the way, anybody can send a message in the chat if you have a question, or just unmute if you have a question, or whatever you want to do. So S2 transmits to S1. So we have S2 transmitting to S1, right? So S2, right, sends out a Ethernet header, Ethernet packet, where the source is S2 and the destination is S1, right? So that packet goes everywhere. It's just sent out here, right? So B1 receives that, and so it learns that S2 is available on that first port, like that. So that's the first thing it learns, that S2 is available on that first port. But it doesn't, this switch doesn't know where S1 is yet. So it's just going to broadcast this out everywhere. We're going to broadcast S2, S1 everywhere. S2, S1 everywhere, right? Well, notably, this way too, but notably in these directions here, right? So that's going to reach the switch. And so this switch, B2, also learns that S2 is available on the second port. So S2 is available on the second port. We're still on this transaction right here, right? We're still here. So in that one go around, it learns, two of the switches learn piece of information. Now this also broadcasts because it also doesn't know where S1 is, but that doesn't lead anywhere, right? Because all those packets are just ignored if it's not the destination, if it's not the correct destination. So that's what happens on the first go around, right? What actually ends up happening in terms of data transfer is like this packet just goes onto this bus and then goes to this, and then that's all the data transfer that happens. This is the only host that actually takes the Ethernet header here, but still we have this communication going on so that the switches can learn the ports. So that's the first one. So I'll erase that. Next one, S5 transmits to S4. S5 transmits to S4. So S5 releases an Ethernet header, which is the source is S5. So this is the source. And the destination is S4. Destination is S4. And so it's going to, release this onto the bus. It's going to hit this router right here, or switch right here. So B2 is now going to learn that S5 is available on port number 1. So S5 is available on port number 1. But B2 doesn't know where S4 is, the destination. So it's just going to broadcast it, right? It's going to broadcast the same message. So that message is going to get broadcasted here. It's going to go here. It's going to go here. It's going to hit this switch. And now this switch is going to also learn that S5 is available on port number 2 of that switch. So S5 is available on port number 2 of that switch. And, we can think about this transferring more, like it is broadcasting more, but we don't care anymore because both of the switches have been talked to. And yeah, so in terms of actual data transfer, what's happening is like the data is just going to go here, broadcast out like this, and then broadcast out like this, and there you go. It's going to hit. That's the only host that's actually going to take the data. So that's that communication. Then S3 transmits to S5. So S3 transmits to S5. So S3 has an Ethernet header, S3, S5. Okay. So immediately this router, or the switch, learns that S3 is available on 2. So B2 learns that S3 is available on port 2. S3 is available on port 2. And this switch also learns that S3 is available on also port 2, but port 2 of the different switch. And that's all. Again, from there, broadcasting happens, but we don't really care because we've already talked to all the switches. Okay, and then keeping on going. The next one is S1 transmits to S2. So if we look at what happens here, S1 has an Ethernet header of S1 is the source, destination's S2. So it reaches here, right? And now B1 gets this header here. It learns that S1 is available on port 1, but it already knew that, right? So we don't have to add that. And it actually does know, it actually does know. Oh, sorry, I said the wrong thing. S1 is available on port 1. So it didn't know that yet. So that's one thing it learns, that S1 is available on port 1. So we do add that. S1 is available on port 1. And now it's going to ask, where's S2? So it actually does know where S2 is. So there's no broadcast that happens here. There's no broadcasting. It just then sends it back because it does know where S2 is, where the destination is. Already has that as one of our first things that we put in there. So no broadcasting. This does not get updated at all. It's just moved like that. So that's an important thing. I'll just put that here, right? On this one, there's no broadcast like that on that attempt. So S3 to S5 for B1. Okay, so yeah, let's see these questions. No broadcast for S3 to S5. Let's see. So S3 to S5. Yeah, there was no, sure. there was no broadcast on that. Still, both of these learned though. Both of these switches still learned what they were like, where S3 is, because of this message being sent on this common channel here like that. But yeah, so like S3 goes to like S3 is sent. So we're going back to this message right here, right? This is source is S3, and then it goes to S5, right? So this switch still received the fact that S3 is available on this side through this port, and this switch right here received that S3 is available here, which it already knew, right, through port 2, or maybe it learned here, and it doesn't have to broadcast it, right? It doesn't broadcast from here. I mean, it's the same as if it just sent it, because there's only one other port, so it's basically broadcasting. But B1 here, B1 also knows where S5 is, so it also doesn't broadcast. But it does learn where S3 is, though, right? It does learn that. They both learn where S3 is, because the switches learn from the source address. So if it receives a source address packet here for a source that it doesn't know yet, then it's just going to add that to its table. So hopefully that makes sense there. Yeah. So there's no broadcast here. There's like no broadcast here either, right? Yeah, there's no broadcast here either. Broadcast here either. But that didn't really change doesn't change the table, right? The table, it still learns from both of them. So hopefully that makes sense. Then the next one, no broadcast on that. So the next one here, S4. Make sure we have everything in order here. Yeah. And then S4 to S3. So S4 to S3. So S4 is going to release a header where it's S4 is the source and S3 is the destination. So that's going to go here. B1 checks, okay, do I know where S4 is? No. So it's going to broadcast that information, right, out like this. B1 does not know where S4 is. And so B2 is going to learn, right, that, well, let me see. I think I'm reading the wrong numbers here. Let me say that again. S4 is the source. S3 is the destination. This is being sent here. It's going to ask itself, do I know where S4 is? No, but I'm learning that S4 is available at this port. S4 is available at port 3. Then it's going to ask, do I know where S3 is? Yes, so it's not going to broadcast, right? It knows where S3 is. So it's not going to broadcast. It's just going to send it here, right? It's just going to send it here. It's going to send this header, S4, S3, source, destination. And now B2 is learning that S4 is available on port 2. So there's no broadcast that happens right here. Right? Here, it's looking for S3. It does know where S3 is. So there's no broadcast that happens here either. Right? So I'll just say no. I'll just say no broadcast. Like that. But there's still learning happening. Just because there's no broadcast happening doesn't mean that the switches aren't still learning about new ports. Yeah, it doesn't really. Well, it affects the MAC table. Like if there was no broadcasting whatsoever, then some of these switches wouldn't learn until later on, right? That's why. But in terms of like right now, these broadcasts, it makes no difference, because if it knows where it's going, then it knows where it's going. It just has to learn based off the source address of what it's being given. So if it's being given a packet with a source address that it has never seen before, that's a learning moment for the switch, where it can say, okay, well, now I know that this source address comes from this port. The reason B2 learns S4's location is because B1 can't send a message to S3. Same line. That makes sense to me. The reason that B2 learns, you want to unmute? You can unmute, Ethan, if you want to unmute.
Yeah, I was just wanting to clarify. So the reason B2 learns of S4's existence is because B1 is, if it could, it would send the message directly to S3.
Yeah.
But because S3 is on the same line as B1 and B2, B2 has to hear that message anyways.
Yeah.
Is that correct?
That makes sense to me. Yeah. That's
Okay.
That's how I understand it. That it's gonna hear it because it's connected to the same bus. Yeah. So it's gonna hear the message. So it's gonna learn from that. Yeah. Okay, there's that. And then we have one final transmission here. It's like this, which is S6 transmits to S5. S6 transmits to S5. So it's going to release an Ethernet header, which is S6 is the source, S5 is the destination. So this is going to get a new value because it's going to ask, okay, do I know where S6 is? I don't know S6, but now I'm learning that S6 is available on port 1. Then it's going to say, do I know where S5 is? Oh, I do know where S5 is. So no broadcast. It knows where S5 is. It knows the destination should be sent through this port like that. So it's just all self-contained in here. But the switch does learn where it can access S6. And that's it. We filled the table. That is everything. That happens in order in this example. So yeah, I can do a quick recap, right? So the way you answer these questions basically is like whenever you have SA, to SB, source A to source B, right? Then or let's say S1 to S2. So source 1 to source 2, right? Whenever source 1 is sending something to source 2, it's creating an Ethernet header, which has two pieces of information. Lots of information, but it has two notable pieces of information, which is that the source is S1 and the destination is S2. So it sends this out. Right? Now, there could be a whole network in between, right? There's a whole network in between these two hosts, right? And the switches there, right? The switches each have a table. And it learns, right, based off of the source address, right? So if it's never seen S1 before, it will now hear this message and write down that, okay, S1 is available through this port. Let's say this is port 1. But if it doesn't know where S2 is, then there's kind of two steps. There's first of all just checking, is the source address a learning moment for the switch? And the second step is saying, okay, well now, does the switch know where the destination is? So if it doesn't, it'll just broadcast this exact header just everywhere, right? And only the host that has the correct destination will actually read it and understand it and properly like take in the data to higher levels. The other ones will just kind of ignore it. So that's the idea, is that it gets broadcasted out from there. So that's what I'm just describing here with an example, right? With just going through like this. So that's it. We filled the table. That is everything there. If there's any questions, feel free to ask. I'm happy to go through. Otherwise, why don't we do a spanning tree problem now, I guess? I have one in my notes that I think I'll go through. Let me find here. I'll just go through the same one that's in my notes because I wrote something for it already. So yeah, if anything. Oh yeah, so after broadcast, it learns S2. Which one? Oh yeah, after broadcast, yeah. Well, not necessarily. Like it'll broadcast this out. It only learns. So this is an important thing. The switches only learn based off the source address. Okay, so it's just going to broadcast this data out, right? And then it's going to get to S2, and that's going to be the one to do it. But there was no learning there, right? The learning only happens based off the source address. If S2 now transmits something, where it's the source, then the switch will learn something. Right? Then the switch will learn something. But the switch only learns based off of the source field, the source information field. This is something I learned today, studying today. So I understand the confusion. But yeah, hopefully that makes sense. So let's take a look at this now. So we'll go through the spanning tree algorithm here for this set like this. So spanning tree. Right. So the point of spanning tree is to get a spanning tree of the graph, right? Which makes the broadcast have less of these cycles in it, and it just speeds up time and all that kind of stuff. Yeah, someone asked, can you please repeat why S4 is learned in switch 2, like from here? So which line are we talking? S4 is learned in switch 2, like this step right here? Yeah, right here. So that's going to be this line right here. So let's see what happens in this line. So in this line, S4 is transmitting to S3. So S4 is transmitting to S3. So S4 is going to have a header, which is source is S4, destination's S3. It's going to go up here. It's going to reach this switch. And this switch is going to first of all say, do I already know S4? No, this wasn't there. No. So I'm going to learn now that S4 is available on port number 3. That switch learned that. Great. But now it's going to say, do I know where S3 is? Yes, I know where S3 is. Right? S3 is available on port number 2. So I'm going to send this packet out on port number 2. Okay. So that's going to get to the switch, and that's going to get to S3. S3 is going to receive the packet. Great. The second switch is also going to receive the packet, which is the same header as this. And it's going to ask now, do I know where S4 is? No, because this line wasn't there. And so it's going to say, okay, now I learned that S4 is available on port number 2. And that's it. S6 to S5, no broadcast. Let's see. S6 to S5, no broadcast. Correct. Yeah, S6 to S5, no broadcast. Yeah. What if B1 didn't know where S3 was? They would broadcast. Then it would broadcast. It'd be basically the exact same thing would happen, except you'd also get the broadcast out this way, but that doesn't do anything, right? Because these would just ignore it. So if B1 didn't know where S3 was, it would just broadcast from there. When S2 transmits to S1, why does B2 receive the packet as well? Because it's broadcasting. So we can go through it. It's fine. So when S2 transmits to S1, so this one, right? So when S2 is going to create a header, which is S2 is the source, S1 is the destination. It's going to send this packet out, right? It's going to send it out from here. It's going to go up there. It's going to go here, right? B2, this is the first one, right? So the table's empty, right? Table's empty. So this is going to ask, do I know where S2 is? No, because its table's empty. So it's going to learn that S2 is available on port number 1. And then it's going to say, do I know where S1 is? Also no. So it's now going to broadcast that same packet just everywhere, including to the switch. Okay, so the switch is now going to say, do I know where S2 is? No, because it's the new table, fresh table. So it's going to now say, okay, well, I learned that S2, the source, is available on port number 2. And then second question, do I know where S1 is? No, so I'm also going to broadcast this out like that. But that doesn't do anything because these are just going to ignore that packet, right? Because they're not S1.
So just to clarify, so
yeah,
B1 would also send it out on port 1. So send it on port.
Yeah, B1, sure. Yeah, B1 would just send it out everywhere. Yeah, yeah. But there's no switch over here, so it doesn't really matter. But yeah, it does. That would be right. Yeah, I'll probably do. People ask me to go over. I don't mind going over at all. I'll just probably do 1 or 2 more, and then we'll move on to the next question. So S5, someone's asking, S5 transmits to S4. So S5 transmits to S4. How about I just take a screenshot of this? Like that's our final answer. And then I'll just erase this. So this is everything here. So that's what's learned after the first transaction. Like that's this. And then now S5 to S4. So S5 right there is going to release a packet. S5 is the source. S5 is the source. S4 is the destination. So that's going to go here, right? This is now going to ask itself, do I know where S5 is? No, I'm learning that S5 is available on port number 1. S5 is available on port number 1. And now it's going to say, do I know where S4 is? Also no, so it's going to now broadcast this out, right? So that's going to reach here. And B1 is also receiving S5 as the source. S4 is the destination. B1 is now again going to say, do I know where S5 is? Right? No, I don't know where S5 is. But I'm going to learn now that S5 is available on port number 2. And now second question, do I know where S4 is? Also no, so I'm going to broadcast this out. No learning on that though, to be clear, on that second stage, right? The packet gets delivered to S4, but B1 did not learn where S4 was there. B1 did not learn where S4 was because it doesn't know. It doesn't know if this was the one that got it or this one was the one that got it. It doesn't know until S4 is the one that actually transmits. That's when we learn. See, that's the last thing, right? S4 is the one that transmits, and then S6 is the one that transmits. So that's why we learned that last. Okay, so I think let's move on now, but hopefully that makes sense here. I can come back to it after if you like. No problem. Okay, so the spanning tree algorithm basically works like this, right? We have this table, right, which is stored in all of the switches themselves. And so we think of like this is a switch A, or I guess like it's not really a MAC, I guess it's more like it is the MAC address, right? It's the MAC address of these switches here, right? So we have A, B, C, D, DA, what am I saying? D and E. And this is kind of how we think of it, right? We have this STP, which I forget what it stands for. STP is the I'm not sure what it stands for, but
Spanning tree protocol.
Spanning tree protocol. That makes sense. And it's just this like this collection of values, 3 values for each of them, and those values are just going to keep getting updated over and over and over again. Okay. And so this is the way we read it, right? We say that like at the start, A, this is all going to be A, B, C, D, E, and that's all going to stay the same throughout the whole time there, like that. And to begin with, A thinks that A is the root with a distance of 0. To start with, B thinks B is the root with a distance of 0. C thinks C is the root with a distance of 0. D thinks D, and so on. Right? So we start with this. Like the way you read this is you say that like A thinks that A is the root with a distance of 0. And then, recursively, these switches are going to keep sending out the STP values, these headers, right? And that's going to update the table over and over again as we do that. So they all start out thinking that they are the root. Right? They all start out thinking that they are the root. So this is kind of the start. It's kind of like around 0 here. Right, so the lowest MAC address will end up being the root through this algorithm. That's kind of the point, right? The lowest MAC address will end up being the root. And basically always throughout this whole thing, the lower MAC address is the one that gets more priority. Like that. They get the higher priority in terms of being the root. So yeah, so now we just kind of copy it. Let's copy it down here, right? So round 1, they're all going to send out their messages, right? So A is going to send out A, 0. B is going to send out B, 0. I'm not going to write all of them, right? And then I'll just write out the ones that are relevant. Okay, so the ones that are relevant here. So this is going to be B, 0. It's going to go down like that. What other one did I highlight? This one too. C is going to send out C, 0 like that. And then, the opposite is true as well, right? Like, so C is sending out, okay, I'll just do this one. C, 0 as well to that. It's all sending around, but let's think about what's happening in all these cases, right? So A is receiving that C thinks C is the root with a distance of 0. But A will reject this message because A has a lower MAC address. Right? We have that here. Like A has a lower MAC address. 2, 3, 4, 5, 6, 7. So this is an order of MAC addresses. I guess I should have said that, right? So this is in decreasing order. Decreasing order.
Increasing order.
Increasing order. Increasing order of MAC. And so that means that A is the real root. A is real root of the spanning tree. So that means that when A receives C, 0, it'll say, okay, well, C is a higher MAC address than me. So lower priority, I'm just going to ignore this message. C, on the other hand, is going to receive the message and say, okay, A thinks A is the root with a distance of 0. Well, like it takes 0 hops to go from A to A. So then A is a lower MAC address, meaning a higher priority MAC address than C is, and so it's now going to change its value, right? So let's look at the table here. Let me just do this. Here we go. So C is going to see this message and say, oh, okay, so A is the root, and it takes me 1 hop to get there because A is a higher priority. C is also going to receive B, 0, 0 at the same time, right? And so it has to choose, but it's going to choose A because A is a higher priority than B, right? Because lower MAC address. So I'm using the word priority here to say, like, I think that makes a little bit more sense to think of it like that. It's a lower MAC address, which results in a higher priority. So C receives both of these, but it'll choose A. That's what it's going to choose because it's a higher priority. And then a couple other things will change as well, right? So like D is going to receive C00, which is a higher priority than its value D. So it's going to be like, okay, so now the root must be C with a distance of 1. Right? Because just add 1 to the 1 hop, right? 1 hop away like that. And then same thing here. E now thinks that B is the root with a distance of 1. E also receives D0, right? Because that's what D originally broadcasted. But B is a higher priority, so it's going to just pick that. So just to be clear, like what changed? These 3 changed like that. These 2 didn't change, right? Because what they received was of lower priority than themselves. So didn't matter. Okay, and then we just do it again. So we don't have to go through all the rounds, but we're going to just keep going. So you go until it doesn't change anymore, right? So for round 2, we take this table and we look at what's being sent, right? So A is still sending AA0. Oh, and I guess, you know what, while I'm going through here, like I'll put my like more cleanly done versions on the side here as well, just so you see the actual final value with everything written. I just don't want to write it again. So that's from my notes there. So then here, right, AA0 is being sent here again. AA0 is being sent here again. C is now releasing, let me go up here, right? C is now releasing this one, or transmitting. Releasing is not really the right word, but C is now transmitting CA1, important because that's going to change B. And then C is also releasing on this path here, right? CA1, like that. So we have this, and what's going to happen is that B is also getting EB1, right? EB1, like that. So this means E thinks B is the root with the distance of 1. Takes 1 hop to get from BD. This is saying that C thinks A is the root with a distance of 1. Now, this is relevant to B, right? Because the priority of A is higher than itself, right? Is higher. And so that must be the correct root, and it must be a distance of 2. You just add 1 to the number. So B is going to change to BA2 from this transaction right there. That's going to cause that to change. And similarly, D is also going to change, because right now D thinks C is the root with a distance of 1. Now C thinks A is the root with a distance of 1. So the root from D must be 2 hops away, and the root is A. So D now thinks A is the root with a distance of 2. Now you can draw all of the arrows if you want, right? Again, that's probably what you do want to do on the test. But just for the sake of time here, I'm just going to draw the ones that actually change things. Like there's also an arrow going from here to here, right? Like that B thinks, well, whatever it was before. B thinks B is the root with a distance of 0, right? That's what it was before. But that's not relevant to C, right? Because C already thinks that A is the root, and A is a higher priority than B, so it doesn't matter to C. So that did nothing. That arrow did nothing. Right? So I'm just drawing the ones that do something. Well, I guess this one didn't do anything either, but just for emphasis. And that's all that changes this round. So I'll just put the complete diagram on the side here. Then we move on. There's only 2 more rounds. We don't have to, there's not that much that happens in each of these rounds. So the next round, round 3, take this diagram. We look at this. Right? The only thing that changes this round, right, is E, because now D thinks that A is the root, and so it's going to transmit DA2. Right now, E thinks that B is the root, but A has a higher priority than B, and so it's going to now think E is going to change now. Right? E is going to change, and E is now going to think that A is the root with a distance of 3, right? Because it was a distance of 2 here, it's 1 hop away, so distance of 3. And then if you do this one more time, nothing will change. And so this is your final set.
Adam, I have a question.
Yeah.
Doesn't B also transmit BA2? And then how does E know to follow B's path or D's path?
I think it doesn't matter, right? Because either way, you're going to get a spanning tree here, right? So you're right. This does also transmit BA2. But either way, what's going to happen now? It just thinks that it still thinks A is the root with a distance of 3.
Okay.
Right. That's the only. It doesn't really know the path. It just knows what the root is, and then I guess you would use some sort of different algorithm to get it. Right. That would be like your last thing. But yeah,
If they had a
like to
different
get the
length,
path.
would E take the shortest length? I assume. So, like, say, for example,
Yeah, like that probably makes sense. Yeah, but regardless, it has to have like at the end of the day, this column has to all be the same number. That's how we know we found the root, because there is only one root of the spanning tree. So that column has to all be the same MAC address.
Was there not some caveat about like ties? I'm not sure if it was ties related to MAC address or ties related to something.
Isn't it that it takes the lower MAC address if it's a tie?
So if there's a tie, it takes the lower MAC address.
Yeah, if there's like a tie in the length, you choose the lower.
Oh, okay. So you're saying that it will choose this path.
That's why it picks B.
Yeah, because there's two ties,
Yeah.
EDCA and EBCA. It will go to B because B has the lower MAC address compared to D.
Yeah. That makes sense, but that doesn't like
change the table,
add
right?
it doesn't change anything to this, but yeah, like in terms of the actual spanning tree, yeah, the actual spanning tree would end up being like here, like that, and then this would have to be connected like that, and then it would choose one of the links here like that, and that would be your, because D at the hop of 2, yeah, there you go. So that would be your spanning tree at this point, or the other link. It doesn't matter. Right? Yeah, makes sense. That's good. So technically, again, you do one more round just to make sure that nothing changes, but nothing changes here, and that is your spanning tree algorithm there. So, everybody okay with this? Any questions? Choose the lower MAC address. Yeah, everybody's just saying chooses the lower MAC address. Yeah. Do I think the prof will ask us to do multiple rounds or just one? I do not know, but do I think? I think possibly be ready to do all the rounds. Yeah.
And are we supposed to also like draw the tree or just the table?
Depends on what the question is asking you to do, right? But I think the table is the important thing. Like that's the actual protocol, like that. Yeah. Depends on what the question is asking you to do, though. But yeah, I think that's the most important thing. We're mentioning that if a link goes down, the whole procedure has to be done again. I can see this happening in the final. Yeah, so that's an important thing to note, right? Someone's saying in the chat here, right, that if one of the links, let's say, it's part B of the question is, okay, but what if this link goes away? I don't know. What if some link goes down? This link here, then the whole algorithm has to be done all over again, right? To find that, and so they all do it. All the switches take part of this in doing the algorithm all over again.
That only applies for links that are currently in the spanning tree, correct?
That sounds right to me. This is Googleable, though. Probably. If an inactive link goes down, does the spanning tree... And maybe this will be ChatGPT-able. Makes sense, yeah. Cheers.
So if a link goes down, do we start from like the previous answer, or do we start from
We start from
like
this. We start from this. Yeah.
But okay, so just completely empty.
Yeah, because it's just resetting the algorithm. It just triggers that again. Just network topology, because that's how you get the most, like, because if the link goes down, then there might be a completely different spanning tree, like a shortest spanning tree, like that we want to use. We don't know if it's going to be similar to the last one, so you just start from 0.
But yeah, if A goes down, then the route is completely gone, so that they
Yeah,
have to
like,
find a
exactly.
whole new route.
Exactly. Like if this is the link that goes down, then everything has to change.
I see.
Right. So it says inactive links are disabled, so yeah, only the active ones. Yeah, that makes sense. If an inactive link goes down, what's the difference? That doesn't change anything because it was already not part of the spanning tree, and so it's not going to now be part of the spanning tree. Yeah. Okay. So only the active ones. Yeah, that's that question.
Adam,
Yep. Mm-hmm.
Technically, in this case, at the once we find the route, obviously, I think isn't the next step to technically deactivate the links, the redundant links, and that's the whole purpose. So in this case, because the distance from E to B is technically smaller than E to D, because the MAC address of B is smaller, we deactivate the link between D and E.
Yeah.
So
in the span, yep, these will go down. Yeah, these 2 links will go down. Or I don't think it matters which one you choose here, but the definitely this link will go down, and one of these links will go down. Right. Yeah, that's right. That's the point of doing all this, is to get the spanning tree where there's no cycles, and then that's incorporated somehow into the broadcasting algorithm in an actual application like this, so that we don't have these cycles. Okay, so that's the first couple questions that I wanted to, well, 2 questions that I wanted to try. I have a couple more before we just start doing the other thing. So there's that one. While we're on the topic of MAC addresses, let's do this question here. I guess I'll do this here. This was from the packet that the professor put together for final exam. I just thought I'd explain this one because it's relevant. So I think I screwed up something here. Yeah, there you go. So consider Ethernet subnet just started up. Suppose the IP address of this IP address right there, 0.23, wants to send a packet to that one with node IP at the node IP with this IP address needs to know the MAC address using the ARP protocol. So all you need to know about the ARP protocol is that there's it's designed to help find the MAC address, right? So the ARP protocol starts with I think I wrote it here somewhere. No, I didn't. Okay. Well, the ARP protocol starts with some sort of request, MAC address request, and this is sent out. This is going to send it out. So that's what it's asking. What is the destination address of the first Ethernet frame out of the subnet? This is just a request, right? This host here just needs to figure out the MAC address of where it's going, and so always that request has a MAC address of just FFF, like all these, right? All Fs, right? Like that's the protocol. That's part of the protocol. The second one, right, will be a response, right? Response. This guy right here is responding with its MAC address because it's said, oh, someone's trying to find my MAC address. Okay, I'm going to send the MAC address. So the next one is going to be the MAC address, that one, the 5823 D7 ... And then finally, this will actually send the message that I wanted to send. 7165 ... So just to color code it, I think it makes the most sense. Let's just color code it. So the first one, A here, is just a general broadcast to everyone. The next, B, is a response from this guy. And then the last one, C, is the message finally being sent like that. So FFF is the only thing that was new here. Yeah, Ethan, what were you going to say?
It's the destination address, so shouldn't we swap the last 2?
The destination address? Yeah, okay. That makes sense. Did I do that backwards? Yeah, I guess I did that backwards. The destination address? Yeah, I guess I'm thinking of the source address. Yeah. So the destination address of the second transaction is going back to that, yeah, and then the destination address of that one is that, yeah. Because the source address of the first one is this. That's the source address of the first transaction. Is this 7165F7, blah, blah, blah. So yeah, I just thought I'd mention that now because we're just talking about MAC addresses. So yeah, why don't we now move on to some other stuff? We could do maybe, and if anyone has any questions, you can always let me know. I think I closed the Zoom window by accident, so let me open that back up. Yeah, FFF is for broadcasting to everyone.
If the destination address is FFFF, then how does it know that it's looking for the MAC address of 237.196.7.14? Shouldn't like how does that work?
That's also there's more information in the packet than just FFFF. Like there's also like the IP address of where it's trying to find. Like of what it's trying to find is also.
That's is that in the header or is that like data?
That's in the header, I'm assuming. Yeah.
Okay.
That must be in the header, right? That it's looking for that. Yeah. So there's more information than just this that's being sent. Yeah. Why is it FFF? That's just chosen by the protocol. That's just the value chosen by the protocol. In general, that's what those kind of boundaries mean. Yeah. Okay. So I'm going to open up what the professor put together, and then we can try some questions in there. So or I guess okay, well we can try some of this. That's that one. I guess we could try this now. These guys, like this one here, where it's like with the windows and the sliding stuff. Maybe this question here, where we draw it. Is that that's not the answer? Oh no, that's the answer for the first. Yeah, I see. Okay, we can try this one. Let's talk about this for a bit. Okay, so it says, recall the mechanism of go back n and consider a simple case of the window size being 4 and a short session of sending 4 data packets. Below is the diagram illustrating the data packets and the acknowledgements and the exchanges, as well as the window on the sender and the receiver side being moved around. Right. So let me mess that up. Let me move it back. There you go. So, did I line that up perfectly? That's cool. There you go. So there you go. So the let's go through what's happening here. So the sender has these 4 packets that it wants to send: packet 0, packet 1, packet 2, packet 3. Okay. So it has a window size, which is how many it's allowed to pipeline, essentially, have multiple going at the same time. So the window size is 4, so it's sending 4 packets as well. Those don't have to be the same, but it is in this case. So the 0th packet is sent, right? And in this case, nothing's wrong. Everything's being received here. This is like normal operation, right? So it received the 0th packet. So the window here shifts over, right? Once the ACK is sent, the window shifts over. So now it's waiting to receive number 1. It'll receive number 1, sent the ACK, waiting to receive number 2, waiting to receive number 3. And then once it receives number 3, sends the ACK for 3, it'll just it'll just move on to the next spot that it wants to fill in the window, which is a later piece of data. Now the window over here, right, always stays the same size. I mean, in both cases they stay the same size. Go back in, right? For go back in, the window size here is always 1. So window size of the receiver is equal to 1 for go back in, and the window size for the sender is some value, right? In this case, 4, right? And so the window size stays the same, and it just kind of shifts over as the acts kind of get received here. So the question is now to say, okay, well, draw the diagram of what's happening if in a couple situations, right? So for the first one, it's really just the window size remains 4, but now there's 5 data packets. So draw the whole diagram now. So I mean, it's not that much to say about this one. It's basically the same as the one before, but let's just go through it, just drawing it ourselves once here, just to be able to do it. Right? But of course, I'll have the solution. Just make sure I'm not saying the wrong thing. So first of all, it's sending 5 packets. So we're going to label them 0, 1, 2, 3, 4. And the window size is 4. So we're going to just label these, right? So this is on the receiver, this is on the sender side, and this is going to be the receiver side here, right? So the first thing that happens is that packet 0 is sent. So PKT0 sent, right? And so then on the receiver side, right, where essentially here is 0, 1, 2, 3, 4, and the window is at 0. It's waiting to receive the 0th one, right? So here it receives the 0th one, fills it, and then sends back the acknowledge, right? So again, we have 0, 1, 2, 3, 4, but now the window is going to be here, right? And it's going to have to move the window. It has to have sent the acknowledge, right? So it sends the acknowledge like this. So this is ACK 0. Okay, but already, right? This has sent more pieces of information, right? This didn't wait. The sender did not wait for the acknowledge to come back. That's the point of the sliding window stuff. The point is that we can just keep moving things over. So if that's sent, right? All right, sorry, the window doesn't move yet. The window doesn't move until we get the acknowledge, right? But it can just start sending the next one, right? So it can just send the next bit here, or the next packet. So it's going to send PKT 1 is sent. And so it successfully receives it, and the window moves over by 1 because it sent the acknowledge. Like this. And so we get ACK0, 1 I mean. And again, this can just keep sending, right? It'll send all 4. So 0, 1, make them a little squeezed together here, 2 and 3. So this will send packet PKT2. And this will send PKT3. And this will just keep moving over because the question didn't say that there was any kind of loss or anything like that was happening. And there we go. We get to the end like that. And then we're sending, yeah. So then now on the ACKs that are coming back here like this, right? So we still have one more packet to send, right? We didn't send all the packets. So we're going to move this here, right? 0, and then 1's the next one to fill, 2's the next one, 3's the next one to fill. 4, do I have these right? So that goes to there, to 1. Yeah, okay. Yeah. This is right. This is right. Yep, everything's okay. So this is now going to send ACK for 2, and this one's going to send ACK for 3. Right? And the reason this is still boxed here is because there's still one more frame that needs to be sent, and it will be placed in spot number 4 on the receiver side. Okay, so now when ACK0 arrives, this is when the frame is going to move over by 1. Right? And this is now also when this the sender can send this last packet. Right? So it's going to send packet 4, which is going to go 0, 1, 2, 3, and 4 is now filled because it successfully got there. And so then the window goes off this window size. And we get this set like this. And the ACK will also be sent. So the ACK for 4 will also be sent. And at this point, it's now just every time an ACK arrives, this just moves over by 1. Every time the ACK arrives, this just moves over by 1 now. So that's for the whatever it's called, the slide and go back in. That's how this works, right? So the ACKs move the windows around. And that's our final That's our final connection there, like that. Okay, so can you do an approach with selective repeat on the same question as well? Yeah, I'll have to remember. Yeah, I haven't done that yet, so we'll do it together. But yeah, that sounds good. We can definitely try that. So that's basically how this works. Now I do still want to do question number 2 before we go into doing selective repeat. We'll go back into this. We'll do that after. But first, let's do the part 2 of this question, which is the same thing, but there is packet loss. Okay, so we have to talk about what's going to happen with the packet loss. So for part 2 here, it's going to be the same thing, but now the first transmission, the first time packet 1 is sent, it's lost. Okay, and then we're going to have to see what happens when that happens. So same thing, 0, 1, 2, 3. So the window size remains 4 datagrams or 4 data packets. So it's not 5, right? We only go same like here, 0, 1, 2, 3. And the window size to begin with, I guess I'll do that in black. 0, 1, 2, 3. And then the window size goes there. Okay, so the first thing is that packet 0 is sent. PKT0 is sent and received by the destination, the receiver. Currently 0 is there, and then now 0, 1, 2, 3. It arrives, is successfully received. This indicates that the next packet should be placed at number 1, and it will send back the ACK for this, right? So I'll do it like a little, let me just see how the diagram looks. Yeah, I'll do it like a little down like this because we have some other things we have to send as well, right? So it's packet 0, and this will send ACK 0. Now the next thing that happens, yeah, question.
Sorry to interrupt, but like
Yeah.
you know when you're doing for go back end, like don't we like send the packets like in the window first before proceeding for the acts for them?
Well,
Or I think it was
so you're saying like I should send all of these first and then send the ACKs?
yeah. I mean that's like the order that I followed in Nesso Academy, but like
Right. Well, this is my understanding of this is how it works. Is that you like each packet has to be sent individually, right? Like these are separate packets here. And then the receiver does have to individually acknowledge each of them. Like that's an important thing because that's what moves this window over. Is that like it's acknowledged that it's been successfully sent.
okay.
So yeah, I think this is fine. What I'm doing here I think is okay. But yeah. Okay, so yeah. So the next one, it's going to just send packet 1 now, right? So it's still 0, 1, 2, 3. I mean, this is going to stay the same the whole time, right? This, not the whole time, but for the first bit here, it's just going to be that because the window's not moving. And it's going to send packet 1, PKT 1, but it's actually going to fail to send, right? So it's going to get interrupted. So packet 1 did not get received, right? So but the sender doesn't know that, right? Because the sender didn't receive an ACK and it's not waiting for an ACK to send packet 2. So it's just going to send packet 2. PKT2, okay? But packet 2, this is still, like this didn't move here, right? The window is still 0, 1, 2, 3, and it's still on 1, right? Because it has not received packet 1 yet. It's waiting for packet 1 to fill the spot. So it will ignore this. Ignored. Right? And then finally, we're still going to get packet 3 being sent here. Oops. Still going to get packet 3. I'll move this arrow a little bit lower. Move this arrow a little bit lower there. There we go. So then here, oh yeah, that's still right. So then packet 3 is same thing, right? It's going to be the exact same thing as this, right? It's ignored because packet 3 can't be processed yet with this, whatever it's called. I keep forgetting the name. Go back in because it's waiting for packet 1 still. Okay, so we do get the ACK for packet 0, right? So we do get the ACK for packet 0. So since we get the ACK, we're going to shift the window over by 1. right? So that's when the sender shifts the window, when it gets the ACK, right? So it knows that, okay, I don't need to think about that packet anymore. I'm just going to move my window over by 1 now. Okay, but now it's just going to indefinitely wait. It's waiting now for ACK1, right? But it's not going to receive ACK1. ACK1 never sent because the receiver never got packet 1. Okay, so there's some amount of time is going to pass, and then a timer will go off, right? Or packet 1 timer. Packet 1 timer. What am I saying? Timer goes off. So when packet 1 timer goes off, then it's just going to restart from right here, right? From this, well, not like the window's not going to go backwards. The window's going to stay in the same spot. But since packet 1 timer goes off, it's going to now resend packet 1 and packet 2 and packet 3, because it's agreed that this protocol, that's how it should work, is that it will now resend all these values. So now it's going to, from this point on, resend packet 1, PKT1, and then we're assuming that it successfully arrives, right? So the window gets shifted over here, and this will send back the ACK, right? The ACK, but I'll leave the ACKs off for now just because it's hard to draw if you put the ACKs there. Let me try to select this. No, not going to be nice to me. So then it's going to send, the window stays in place, right? Because it didn't receive an ACK yet. So the window's here. It's going to resend packet 2. Oh, wrong color. PKT2. It's going to successfully arrive. Packet 2 is now going to, I mean, the next available spot is going to be packet 3. And then again, it's just going to do the same thing here, right? So then packet 3, PKT3 is going to send. And this is going to go off the edge like this, right? So this is now going to go off because it's sent the whole sequence. So it's going to go back to 0 really, but it's going to send the whole sequence there like that. And now it's going to get, this is going to get the ACKs back, right? So the ACKs are going to come back like this. So ACK, this is ACK1. This is ACK0. And the ACK1 was the whole thing that we were missing last time, right? ACK2 and ACK3.
Do we always assume that the entire window sends before the first ACK comes back?
Do we always assume that the entire window sends before the first ACK comes back? Yeah, it's that's a good question. It seems like it based off of the solutions that we've seen here.
Yeah.
Right. So maybe we're just meant to assume that transmission. Yeah, that transmission is just way faster than the ACK coming back like that. Like just the set, because it's probably like there's not very much wait time between these sending, right? There's no transmission delay because there's nothing transmitting like from here to here,
sense.
right?
Mm-hmm.
There's nothing transmitting. There's nothing to wait for. It's just you just send the next one right away, right? Because that's the kind of the point, right? We don't have to wait. So yeah, so that's that. So yeah, here we go. This one. Now we get the ACK. We'll move it over. Again, we get the ACK. I'll just redraw 1, 2, 3. We get the ACK. We'll move it over. And finally, 0, 1. 0, 1, 2, 3. We get the ACK. We'll move it over. And there we go. It's done. We've successfully done the whole transmission with a failure in the middle there, right? And the point is with the stop and go, whatever it's called, go back in, there's a timer that's going to go off. And that's what's going to trigger it to actually now complete, to restart the transmission of whatever timer went off. Technically, there will also be timers for 2 and 3 that are going to go off, but it's the first one that's going to go off is going to be for packet 1. And so again, assuming here, probably those timers are reset for 2 and 3, right? Because we've resent them. Like at the time of sending, that's when the timers are reset. So yeah, that is that. That is our go back in kind of procedure here like that. We can try this as well with selective repeat, unless there's like a better question to do with selective repeat. You know what I mean? Like, so let's take a second here. If anyone has a suggestion for like, if you did one in the lecture, that might be good for us to do. We could just do this one with selective repeat. That's also totally a possibility, and that's totally fine. I'll just see quickly if there's any one that he did, or there's any other examples that could be good. Yeah, so someone's saying if ACK is lost, right? So if ACK is lost, that's a good question. So if ACK is lost here, how should I show it? Let's say this ACK is lost, this one here. So on the receiver side, right? Receiver side, it's going to get these other ACKs, but it's not ready to move on. These are going to be ignored now because it's not ready to move on because it hasn't ACKed this one yet. So the timer will go off for this one and it will resend. It'll resend all of these. Now there's going to be duplicates over here, right? But that's fine because they're sequenced. The values are sequenced. So there's nothing's going to get confused because it knows what it's waiting for. It knows it's waiting for the next one here, right? So it'll just send it and then send it back like that. And the ACKs will come back like this. So here the timer will still go off and the duplicates here will be handled properly because it's sequenced. Like we know 0, 1, 2, 3. That's the order it's supposed to come in. So there's not going to be any kind of confusion with what's happening there like that. Now there could be confusion if like there's a 0, like the 0 here and the 0 here, that gets confused. And I think I forget what it was, but I think like the window size should be half of the total amount of data packets that's being sent, right? So that's in the lecture somewhere. I'm pretty sure that it should be half the size of the total number of data packets. Or maybe I read that in some online somewhere. Yeah.
This is the minimum sequence space size is equal to double the window size.
Yeah.
For selectivity.
Yeah.
Same thing as
window size is equal to double or other or
no, the sequence, the minimum sequence space size is equal to 2 times your WS.
Yeah. Min sequence size equal to 2 times the window size of the sender. Because otherwise it can get confused because of missing ACKs and stuff like that. So that's kind of the rule here, and then that doesn't happen anymore.
So Adam, really quick question.
Yeah.
For the one scenario where the acknowledgement doesn't come back, obviously the window on the left side won't move over because it doesn't get the acknowledgement. So and then obviously the timer will go off and then it will reset at that specific one the timer went off. Does the receiver know to also reset back to that same number? Like, is there communication between the send and the receive side? Like, how does you said there's duplicates, but how does the receive side go back to starting at, like, for instance, 1?
Yeah, so I don't think the window ever has to go back. Let's just draw it and let's see what happens. Like let's draw it here. Right? So if I send 0, 0, 1, 2, let's just say I send this, right? Or whatever 3 as well. And then the window size is all of them, right? So then this is sent. And so then here we get 0, 1, 2, 3, right? So this is now here. The ACK goes back, but it gets lost. Okay. But then this one also sent all the rest of them, right? So this sent this and this and this. Oops. This. All of these were sent. Right? But it's waiting for the ACK to come back. So this did progress, right? So this goes 0, 1, 2, 3, 0, 1, 2, 3. So these, oh no, sorry, that goes there, that goes there, and that goes there. Let's say all the packets did successfully get sent, right? And the last one here, right? Now this is still waiting, right? This is still waiting. It's going to send ACKs like this, coming back like that. Oops. Like this. It's going to send ACK 1, ACK 2, ACK 3. ACK 1, ACK 2, ACK 3. So from here, the sender is still waiting for ACK 0. So the window does not move over. Now, it's waiting for ACK 0. So when it gets ACK 1, ACK 2, ACK 3, I'm fairly certain it will just ignore that. I think cumulative acknowledgement is for the other one, for selective repeat,
Yeah.
right? Yeah. Yes. So here it's going to get so it's going to ignore these acknowledgements, and then there's just going to be a timer that goes off that says I didn't get ACK 0, so I'm going to resend the packets. Right? I'm going to resend the packets. So some timer timer 0, right? It's going to resend the packet 0, and then this is going to ACK that it got packet 0, right? Because it is already way here. Well, okay, so actually, pretend the data set goes a lot longer, right? Because this is technically 0 here, but that's the whole point, is that why we need the window size to be half the sequence size, right? We need it to be half there. So pretend this goes like 4, 5, 6, so this isn't 0 here, right? So it knows that, okay, it already got 0, so it's going to send ACK 0. It's going to send ACK 1. It's going to send ACK 2. It's going to send ACK 3 because it already got it. It knows it already got it, right? It doesn't, and it's not going to take in that data at all. It's just going to discard it, but it's just going to send the acknowledge back so that it knows, so that the sender knows that it has been received. Like that. We can look at some notes here. Here, there's a good YouTube video that I can kind of talk over a little bit. Let me open this up. So we're not going to literally just watch the video, but I'll mute it. Oops, did not mean to do that. Let me go back here. So we can kind of talk over this here. So go back and in action here, right? So, by the way, I'll put this link in the chat in case everybody wants to take a look. Obviously, it's better to watch the video than hear me talk over it. So let's see what's happening here. Let me skip forward a little bit. There we go. Okay. So is that the end? Oh, went too far. Just see the animation one more time. There you go. So window starting out 0, 1, 2, 3. Sends this packet, packet lost, right? Doesn't receive the ACK. We don't receive the ACK for packet 2, right? So timer goes out. Sure, we get the ACK for we don't get any ACK, right? Okay, so it looks like the receiver resends whatever is the most recent ACK that it has received. Resend ACK 1, resend ACK 2, ACK 1, resend ACK 1, right? When these things go on. So the window can move on by 2, right? The window can move on by 2 here because 2 of the packets did get received. It's the third one that got lost. So after the timer goes out, then we get this, and we get the same thing happening. So this is like my diagram that I drew there, right? And this is selective repeat. I thought he did an example where there was the ACK was missing, or was it? Did he do it here? No, he did it here where there's just a packet loss. Is it in the next video? No. This is just TCP stuff. Okay. If you haven't seen this guy's stuff on computer networks, it's very good. Definitely recommend it. It's a lot of good content. Okay, so yeah, maybe we can look here, like go back and if ACK is lost. Let's see if there's a nice diagram that kind of shows it. So that's still with the packet being lost. Packet being lost is okay. Packet being lost is okay. No. Okay, here the ACK is being lost. Sliding window protocol set to receiver side. Okay, maybe this is relevant. Let's see where this comes from. Okay. So this is go back 4. Window size is 4. Okay. So ACK 4 is lost. So 0, 1, 2, 3 is sent. Discarded now as receiver is expecting packet 4. So these are all discarded here. So we see that 4, the ACK is lost here. Why would ACK 4 be
You can use cumulative acknowledgement. That's what's happening here.
Cumulative acknowledgement, as in like it's saying all 4 is being acknowledged at the same time.
Yeah, that ACK4 that's missing is a representative, I believe, of all 4 packets.
Okay. Okay. One extra sequence number. Yeah. Oh, okay. Because there's 5. Okay. Yeah. So, but it does resend it, right? As what I was saying before. Like it will just resend the packets that it doesn't get, that it has been act for, and then these are discarded because it's still waiting for. It's still waiting for 4, but I guess it's waiting for
packet 4, right? Packet number 4.
I guess so. Which would be the first one of this next sequence here, because
no, it's retransmitting those 4 because it never received the acknowledgement, right? And so it's expecting packet number 4, but the sender has to retransmit 0, 1, 2,
0, 1, 2, 3. Oh, okay. Yeah. So those are all going to be ignored.
Yeah.
Okay. Well, there's that. So why don't we try some of the selective repeat stuff, which I'll probably, let's maybe talk over this diagram first and see what happens, right, in this kind of thing. So we can look at this after, right? And then let's see here, right? So for selective repeat, let's just go through what's going on here, right? So again, we have our window size of 4 and then our data size of like 9 here. And so the which satisfies the whole condition that I was saying before, which is that the window size has to be half the sequence space size. So packet 0 sent, packet 1 sent, right? Doesn't matter. We sent packets, receive packet 0, ACK 0, we got that. Packet 1, ACK 1, we got that, right? So then that moves the window over. Same as usual. So if the packets are sending properly, same stuff. Now, packet 2 got lost. So we never received packet 2. And so we don't send ACK for packet 2, right? Because we know that because this receiver never received it. But we do receive packet 3, and so that's just stored in a buffer, right? That's just stored there. And it does send the ACK back. So we know the ACK is ACK 3 has been received, and so we don't have to resend that, right? So then here, after packet 3 was received, ACK was sent. Then what happens here is that these ACKs got back, and so it can send packet 4, packet 5. That's totally fine, right? But it can't move on to packet 6, right? Because that would require receiving the ACK for packet 2. We haven't gotten that, so the timer goes out. These just, receive, get put in a buffer. The timer goes off, we resend packet 2, and then all of this stuff can deliver, right? We can deliver packet 3, packet 4, packet 2, packet 3, packet 4, packet 5. Deliver means actually receive into the receiver. Like whatever this process is that's receiving, it can actually take it and then send the ACK for 2. It doesn't have to send the ACK for 3, 4, and 5 again, right? Because it's already sent those ACKs, right? And then what happens here is that this window is just going to now move over a bunch of times, as much as it can, to go to the next spot there like that. We can kind of see it happening here. We can see the kind of the more of the algorithm here. So we have a timeout, right? So if the next available sequence number in the window send the packet, that's what we were saying here, is if the sequence number is available, send the packet. So why don't we do, it makes more sense, I think, if we just draw it. So let's do that. I'll do maybe, let's see here. So why don't we start with, someone said window size 3. Sure. Like we can send 0, 1, 2, 3, 4, 5. And then window size 3. So we're sending these 3 at a time here like that. Oops. Like this. And then again, we can say, I just want to make sure it's a good example, right? That's the thing. So it's like we can totally make it up, but it might end up being an annoying example. So let's see. Maybe I can find one here. Selective example. So let's see here. So if it's all working properly, then it's just going to send ACKs back. So we're not going to draw one where it's working properly. It's just going to send the data and send the ACK back. But let's see here. Maybe there's one that's good. Or if anyone has one from the lecture or something like that, that's good. Okay, let's look at this. 0, 1, 2, 3, 4, 5. Frame size is 2. Look at the scenario where a frame is lost during the transmission. So we'll say that frame 2 is lost. Okay, so we'll say frame 2 is lost. So we have this scenario here, right, where we're sending. So we're sending packet 0 is being sent, and then over here, we're also receiving the correct packets here, right? So this receives. I guess I'll just say receive RCV. Packet 1, 0, I mean, and it sends back the ACK for this, like that. So this is ACK 0, and then it also at the same time sends out packet 1, like this, packet 1, and this receives RCV packet 1. Okay. Now, it has to wait, right? So it has to wait because the window size is only 2. So it's going to wait for these to come back, ACK 1. Once it does receive these, right, these 2, then this can move over by 1. And this can move over by 1. I mean, another one, right? Okay, so now it's going to send packet, let's see, interactive. That's good. Oh, okay. That's cool. Yeah, let's do that after this, but we can definitely take a look at that after. That's cool. So now let's say frame 2 is being sent, right? So we're sending packet 2, PKT2, and this is lost. Okay, this is lost somewhere. Okay, so it never receives it, and it's at the same time we're gonna send packet 3, which does send, right? PKT3 is being sent and is received here. So let me see here. We didn't receive this. Yeah. Okay. So packet 3 is going to be received here, and we can say RCV PKT3, right? But then the ACK that's being sent back. So here the ACK that was being sent back is for 1. Here the ACK that is being sent back is for 1. I'm fairly certain that this will send back ACK for 1 as well. Again, let me compare that back to this, right? Where are we? Where's the video? Oh, here's the video. Send ACK 3. Oh no, it'll send the ACK for 3 because it received 3. Okay, received 3. Then from here, this sender is now going to be waiting. So packet 2 send after ACK 0 only and not ACK 1. So packet 2 sent. Oh yeah. After the ACK 0. Oh yeah. Yes. Yeah. Like this arrow should be a little higher. Sure. Yeah. This arrow should be a little higher. Like that. Right, because it moves over with the ACK. Yeah, that's fine. Didn't receive. We get that ACK there. Now, on the way back, we do get the ACK like this. That comes back like this. So we have ACK 3 that comes back. But the window can't move forward, right? So we just get a timer that goes off like this. Let me see. Let me compare back to this picture here. Right. So we get a timer that goes off. P2 timeout. Yeah, same kind of ordeal. We get a timer that goes off. So ... So here it's still this. Right. So then ... timeout. Right. Timeout for 2, and then it resends 2. Resends 2. And let's say that successfully goes RCV packet 2, and it will send an ACK for 2. ACK for 2. Right, and so now we get that ACK back here. ACK for 2, and also an ACK. No, an ACK for 2, and that's it. Yeah, an ACK for 2. Yeah, and then this just moves forward because both of those have been acknowledged. So then this will go to here, and then it'll continue from there normally. This will go like that. These will be sent in order.
Hey, just a
Receivers.
quick question.
Yeah.
Yeah. Not bad to interrupt again, but for this, like, I want to confirm if the data in the scenarios where the data packet is lost and the acknowledgement is lost, the scenarios will be like the transmissions itself will be the same, would it not? Like the sequences, regardless, like according to the stop and wait, which is like the go back in or like select or repeat is based off of, like if you don't get it within the timeout back, like it's just going to resend it.
Yeah, it's just going to reset. Yeah, that's like that. If you don't get the acknowledged back. Yeah, so you're saying it doesn't matter if it's the acknowledged that fails or if it's the packet that fails itself?
Yeah, that's why I wanted to clarify like those two scenarios. Like it wouldn't change the actual the actual arrows, like sequences of events.
Yeah, like from the sender side specifically, it would be the same thing, right? From the sender side, for sure, it would be the same thing. From the receiver side, it's going to receive some extra packets that it doesn't need, and it's just going to have to ignore those. Right? That's the only thing, right? So but yeah, I guess that wouldn't change the arrows though. Right? That wouldn't change the arrows that are going back and forth. So yeah, that makes sense to me. Some questions here. Doesn't packet 2 send after? Oh yeah, we said that already. The receiver's window moves upon receiving, and the sender's upon ACK. Yeah, that makes sense. That's how I am approaching it. That is how the rule I'm using in my head, right? That it's basically when the receiver sends an ACK, that's when it moves, and then when the sender receives an ACK, that's when it moves. So the window only slides when the ACK receiver 2. Yeah, that's right. And we just kind of record that this has been, even if Act 3 is sent first. That is my understanding. That is how that works there. Yeah, because you just the system just records that Act 3 was received, and then we'll use that to move it twice here. But you can't move past the 2 yet because we don't know that the 2 has been delivered, has been actually successfully received by the receiver, and so we need to potentially resend it so the window can't move past 2 without the ACK. So someone said an interactive thing here. So why don't we try it? I don't know. Let's see what this is. So selective repeat protocol lab. The sending window limits the sender to a maximum of 5 outsending. Click send new. Send new. So this is the sender. This is the receiver. So this was sent. And then the ACK received. Yeah, we can do a subnetting question. Okay. Great. So send it again. Let's go a little faster. Can I click it a bunch of times? Yeah, I can click it a bunch of times. So this is the selective repeat, but how do I maybe can I kill this one? Okay, let's say that one dies. Then what happens? Is it gonna, after some time, resend? Okay, let's say send new. Send a couple new ones here. Buffered, ACK. There. Let's say I did all this, right? So these ones are buffered. So they're not ignored. So that's the difference. Like go back n would just completely ignore these, right? So I can't send a new. I can't. Okay, what can I do now? Okay, there you go. Finally, timer went off. So that sends back. Okay, yeah. So timer went off. That sent the packet again. Successfully received it. And now you see all of these went to received, right? All of these went to received. And now we can continue sending here, right? So the ACKs don't need to be sent again. This has been recorded that it has been received. And so then these are all ACK received instantly like that, right? Let's see again how that works. Let me just pause and then click this and then kill the packet and then resume and then see it here. So let me just go faster a little bit here because it took like 20 seconds or something. There you go. So the moment that got there, right? These all went blue, ACK received. These were blue already because ACK received was received for these, right? But then the moment that the packet got here, these all became received. And so we can resume and then we can go from there. That's cool. That's a cool little simulation thing. So I'll just put that, I'll just save this in the tutorial document here. Right? That's a fun thing to play with. For selective repeat. Yeah, I can send it in the Discord. And yeah, okay. So that's selective repeat and this kind of stuff. Yeah, CSMA CA, we can talk about that. And then we'll talk about subnetting as well. So yeah, let's move on to kind of that other stuff. Let me open up an example here. Yeah, someone said, can you summarize the difference between selective repeat, go back, and TCP? So these are all ways of just kind of dealing with pipelining. So go back and selective repeat are ways of dealing with pipelining. So instead of just waiting for the ACK, going back and forth, we like just sending a packet, waiting for ACK, sending a packet, waiting for ACK. You can just send multiple at a time, and this increases the bandwidth and increases the utilization, of the system. Now, go back N is going to ignore any packets that it's not expecting. So if we lose a packet with go back N, the receiver is just going to ignore the next packets. And then a timer is going to go off, and then all of it's going to be sent again. And that's how it's going to go like that. With selective repeat, you don't have to resend everything, right? Because these were already received here, right? The packet 2 and 3, right? So packet 2 and 3 are being resent here, right? But they were ignored the first time. So you don't actually have to, you could have just saved them and then use them later. And that's what selective repeat is. It's just saving them. And then still you have to wait for that packet to be resent. Still a timer is going to go off. You got to wait for that packet to be resent. And then it's going to be, those other packets are going to be used. They don't need to be resent again. A TCP is more of an overall thing that we're talking about here, where it's just like a connection-based communication between the two. Pros and cons for each method. I mean, I'll just Google this. I don't know, right? Let's see. I mean, just off the top of my head, I mean, there's always a thing of like easy programming, right? So easy programming is one of them. Yeah. Yeah, let's see. Pros and cons of go back N and selective repeat. Okay, let's see here. You don't have to read all of this, obviously, but go back N retransmits all the frames that are sent after the frame which is suspected to be damaged or lost. Retransmits only the frames that are suspected to be damaged or lost. Simpler, more complex. Let's see if there's a conclusion here. Selective repeat is more efficient as it does not waste network resources. Go back N is more used because it's less complex to implement in the network. comparatively less expensive as it requires less storage. That's true. That is something that I didn't think of, right? But like selective repeat, you got to store the packets that are not ready to be actually put into the process, the receiving process. They just have to kind of wait there, waiting for that packet. And so there's storage concerns there, I guess, right? Storage concerns that's probably to us seem probably easily manageable, but I don't know if it's actually manageable on the implementation scale here. But yeah, so that's that. Receiver window and selective repeat can move back. Yeah, the receiver window, I'm not quite sure how to draw the receiver window in selective repeat. Because, yeah, it does seem like it has to go back. It does seem like it has to go backwards. That doesn't quite make sense. So, I mean, I'm not sure. I'm not sure about how to draw that. So I just drew it like this. I just said receive, receive, receive. Okay, so why don't we move on? Let's do some of the wireless stuff, the CSMA stuff. So let's see. Let me open up my notes here. Where'd my notes go? Oh, there. And we can try. I guess I had one question here planned, so let's just try this, right? From here. Too many tabs open. This one? No. Okay, I'll just open it up again. Okay, so we can maybe look at this here, and this is going to give kind of a nice overview of the thing, and then we can talk in more detail, right? So it says, okay, consider the scenario shown to the right in which the lines at the top of the figure show the radio range A is heard by B only. You don't have to read the whole thing, but you can see the ranges here, right? So this is the wireless range of A, wireless range of B, and so on. Then we see these different things happening, right? So at T0, D sends request to send, which is part of the CSMA CA kind of thing. So we sends a request to send. D sends a request to send to C. And C says, okay, no one's sending to me right now. I'm going to say clear to send. Now, clear to send goes to everyone, right? Clear to send goes to everyone. So everybody in range knows not to send to C at the moment. Clear to send. Okay, once the clear to send is received, D will send the data. And it knows that it's probably safe because the C is set to clear to send, so it knows that nothing else will be sending to it except D. Now that only is valid for a certain amount of time. A then, in the middle of this data transfer, wants to send a message to B. So it says a request to send to B here, but B doesn't respond. Right. So in the meantime, node A sends a request to send to B at time T1. B can't respond. B can't send anything right now because of the clear to send message, like that. So there's a couple questions here. So let's maybe talk about these. So it says if node A were to begin transferring to node B at some point after T3, would A's transmission interfere with the ongoing data transmission? So basically, if A did not receive a clear to send, but if it just anyways sent data here, sent its data, that would actually be fine, right? Because it's not interfering with this data transfer. It's not in the range of C, right? It's just here. It's also not interfering with B because B isn't actually doing anything. B is just idle. So it could be receiving data, but it has no way of signaling that it is allowed to be receiving data right now because of this whole clear to send RTS thing. So no, right? Would A's transmission interfere? It would not interfere. Let's look at B. At T3, can B respond to A's RTS message with a CTS message? Why or why not? So can B respond to A's message? So the answer is no, right? Because it has to wait because of this clear to send. I mentioned this before already, but it has to wait because of this clear to send. So it can't send anything right now. Because if it sent a clear to send, CTS, right, it would collide with this data, right? Because C is also receiving it. So it would collide with this data transfer here, and that would be no good for C, right? It would be jumbled at C. Yeah. So no. That's it. In the 801.11 protocol, which is what we're talking about here, this CSMA CA thing, what will node C do at T4? What will C do at T4 at the end of the receipt of data from node D? And so this is how B, either a timeout or B will know that it is allowed to transfer, right? Is that C will then send out an ACK as a broadcast. Right? It'll send out an ACK here as a broadcast. So this is ACK. Okay, and this acknowledges that this finishes. Does C send a confirmation once the data transfer is complete? Yes, it does right here. So once the data transfer is complete, then B knows that, okay, it's free now. It can communicate on the channel because C is not going to be disturbed by that. Or there's a timeout as well. Yeah, we'll talk about that in a second. Let me just answer this last question. So then the question is saying if A, well, I can't show the whole thing because if A were to begin transmitting to node B at some point after T3, if A were to begin transmitting to B at some point after T3, would A's transmission be successfully received at B? Justify your answer, right? And so the issue is that we don't know how long it's going to be till the ACK, right? That's the issue. So notice here, right? What if this data transfer took a lot longer, right? What if this data transfer took this long, right? Then the ACK is going to collide with the data once the ACK sends. So that's why you can't, like, even though technically in this time it would be fine for A to send the data, we don't know when that ACK is going to arrive, right? A does not know when that ACK is going to arrive. And so it cannot just start sending because it might be a collision at B with just specifically the ACK signal there, like that. So that's kind of the problem. That's the issue there. So someone's asking here, is this the exposed terminal problem? So exposed, let me just see the definition of the exposed terminal problem. So it's basically the idea is, let me get a picture up here. I mean, yeah, it is, but get this picture up here. Is that going to paste? No. Right. So the idea is that, well, yeah, it makes more sense to just talk about it here, right? But yeah, so if C wants to transmit, right? If C wants to transmit data to D, or other way around, if D wants to transmit data to C, it has to make sure that there are no other terminals, right, that could be also transmitting to C. That's the problem, right? And so the definition of an exposed terminal is a node that is not the destination and is a node that is not, did I write that right? A node that is not the destination and is visible to the source but not visible to the destination. Okay, so let me just draw that. So a node A, B, and then C, like that. So a node, let's say A is transmitting to B. A node that is not the destination is visible to the source, right? So let's say this is, in the range of A here. Right? Let's say this is in the range of A. That's for A. But not visible to the destination, like that. So that's the range of B, like this. But that would be fine. That wouldn't mess with the transmission, because A could still transmit to B here. B could not transmit to A, but that's not what's happening. Do I have the definition right? let's see if I have the definition right. Exposed terminal.
Yeah, so like the exposed terminal, basically like I just like think it as like I consider from the center point of view, from the center point of view, and like in this case, C is the exposed terminal of A. In this case.
Yeah, C is the exposed terminal A, but that's not an issue in terms of the transmission from A to B. right? Because because
Yeah.
A can still transmit to B, no problem, regardless of what C is doing.
It's just C will hear A's RTS,
I
and
see.
then
Yeah, right. So it could be affected if it was also trying to receive something. It could be affected by this transmission here.
yeah. So like that's why it said in the notes it's kind of an informal issue. It's not a huge serious issue. But
Yeah.
if C is like able to hear A's RTS but not B's CTS,
Yeah.
that means that like it's less likely that if C were to have some other transmission or something, there's still a small likelihood that that RTS will impact the
C.
transmission. So that's why
Yeah.
A should send a short frame to C once A receives its CTS from B. But he didn't go too in depth on it afterwards. He just left it.
Okay, so it's probably not that big of a deal. Right? I mean, hopefully that means that it's not too big of a deal, right? But yeah, that makes sense what you're saying there, right? This probably will tie things together here. If I just do this example, identify the hidden and exposed terminals if so and so. So if D transmits to C, right? Then we're looking for the hidden and exposed terminals. So the exposed is something that is not the destination, is visible to the source, but not visible to the destination. So that's something that's exposed. So F here is visible to the source. It's not the destination, but and it's invisible to the destination, right? So the exposed is F here. Now the hidden terminal, I'll read the definition here. A node that could, why don't I put the picture here of what I'm saying? A node that could also be transmitting to a destination node while being invisible to the source. So something that could also be possibly transmitting to C at the same time. And that would be B here, right? B could be transmitting to the source here. So that's the hidden node is B. Then for C transmitting to D, right? The hidden node, right? Again, we just did that one, so let's do it again. The hidden node is F, right? Because F could also be transmitting to the destination, but C can't see it, right? Invisible to the source. Can't see what F is doing. Well, I guess the circle's not big enough, but yeah, can't see here. So that's that. And then the exposed is something that is not, something that is in range of C, but not the destination. Let's say that, right? In range of C, but not the destination. So that would be B, right? Exposed B. Something in range of C, but that's not the destination. Something that could be screwed up by this transmission. So that would be that. Yeah. So that is that's that example, right? Okay, guys. Well, it is 6 o'clock. I do have something after this, so unfortunately, I think that is where I have to end it for today. I wish we could do more questions, but I think we did some good stuff here. It's not all the easiest things. I'm also learning this at the same time, right? So there's some stuff that's a little confusing, but I think we had some good discussion, and some of these examples were good. And then the simulation link is pretty cool, so I'll definitely play around with that a little bit to help understand selective repeat. Otherwise, yeah, that's pretty much the time for today. So I'll stick around for a few more minutes. I'll stop the recording. Yeah, someone asked if it's recording. Yes, I definitely am recording, as information's at the top here, just on my YouTube channel. I'll post the recording right now. It takes some time to process.